Problem is that concrete is essential in construction, but mixed design today is manual, rigid, and environmentally costly. So engineers also struggle with machine learning tools that aren't really flexible or easy to understand. So our solution uses ChatGPT with structured prompts based on ACI standards. It pulls real mixed designs from a database and also allows interactive dialogue. This way, engineers can get flexible, explainable mixed recommendations tailored to real-world project needs, if any.
Okay. So our main project goals is one, we wanted to apply ChatGPT to scenarios that can assist in concrete mix design. Specifically, we wanted to create a system where users can describe their construction scenario, like needing a high strength mix for a coastal foundation, and have ChatGPT interpret that and recommend a suitable mix. Second, to make this possible, we wanted to embed domain knowledge by using the ACI guidelines and best practices, and also mix the real world data into the structured prompts so that the model can give uh, technically sound suggestions. And another key focus was to enable rationale generation. So we want the model not to just suggest a mix, but also to explain why it chose certain materials and how it balances trade-offs like strength versus durability. Next slide, please. So the first step in our methodology was to define the use case. We start by identifying common construction needs, such as marine foundations that require high durability or pavements in cold climates that need freeze-thaw resistance. And we want to translate these construction scenarios into clear language that the model can easily understand. And we do this by prompt engineering, which is where we structure the prompts by embedding ACI standards. We also standardize the input and output to include material proportions, and also we ask for the rationale. So example prompt is given below is given a scenario, recommend a concrete mix with proportions and explain your reasoning. Next slide, please. So the next step was to build the domain knowledge base, and we did this by collecting sample concrete mixes with performance data. And as I mentioned earlier, we use the ACI standards in which we found online in PDF format, and this was ACI 211 and 318, which was for durability and compressive strength. And we also organize this information in Excel or CSV format, and we reference and embed this data into ChatGPT prompts for uh, proven decision making. Next slide, please. So once the user input is received, the ChatGPT will parse the user inputs into technical requirements, and will generate this into a very structured table, which I will show an example of in the later case studies. But um, basically, it also allows for interactive refinement as well. So if we need to ask follow questions for missing information, ChatGPT will provide responses for that. Um, but yeah, overall, this methodology allows ChatGPT to understand the whole scenario and give a very good technical answer um, to this use case.
So for our project, we used three primary resources: the UCI concrete compressive strength dataset, the ACI 211 standard practice, document 1, published in 1991, and a summarized durability guideline from the ACI Building Code 318 2019 editions and the ACI specification 301 published in 2020. The UCI dataset provide 1,030 sample with key features such as cement content, water, aggregate, blast furnace slat, fly ash, superplasticizer usage, and curing time. And our primary goal to understand the concrete mix behavior, predict compressive strength, measure in megapascal, and assess durability performance, and to kind of support the developments of durable and realistic mixed design, we reference ACI 211, which provide industry standard guideline for selecting proper concrete mix proportions and also integrating the critical durability requirement from the ACI 318 and ACI 301, focusing on exposed classes related to chloride attacks and freeze-thaw cycle, two major durability concern for real-world structures. Next slide, please. In analyzing the UCI dataset using the feature distributions, we found that most sample represent typical 28-8 concrete mixes, which cement contain between 300 and 400 kilogram per cubic meter, water contained between 150 and 200 kilogram, and compressive strength mostly ranging from 20 to 60 megapascal. However, we also identify important outliers, including mixes with extremely high cement content, excessive water content, and curing ages beyond 365 days, suggesting that the inclusion of high performance or specialized concrete. And then using the box plot, we confirm these outliers, particularly around superplasticizer dosage and curing time. These variations highlight the need for careful data management to kind of maintain the model accuracies. Next slide, please. Finally, the correlation heat map validated expected material sign principle, the cement contain and curing age, both positively correlate with strength, while the water contain negatively correlate with strength. Aggregate contain show only weak correlations. That hence it's kind of reinforce the paste quality. Primarily the cement and the water drive the compressive strength. And overall, by combining the insight from the data and the industry established standard, we able to find the most optimized and engineering sound solutions. And on to the next slide is when we talk about our case studies.
So using these datasets, we explored three use cases. The first use case involves generating mixed recommendations for different applications. By following the ACI standard practice for selecting proportions for normal, heavyweight, and mass concrete, ChatGPT can generate corresponding mix designs when the compressive strength requirements is provided. The table shown summarizes the ACI standard practices applied for this purpose. Next slide. For the example result, we asked ChatGPT to generate concrete mix designs to meet a minimum compressive strength of 40 megapascal. The ChatGPT provided tailored recommendations for these three applications. It adjusted the water-cement ratio, cement content, and aggregate proportions based on ACI standards. For example, it suggested increasing the use of coarse aggregate to enhance density in heavyweight concrete and reducing the cement content while incorporating fly ash to control heat generation in mass concrete. This demonstrates how the ChatGPT can quickly adapt mixed designs to meet different engineering needs. Next slide. The second use case is predicting compressive strength over curing time. By providing a specific concrete mixture, we asked the ChatGPT how the compressive strength will develop over time. The ChatGPT follows 4 steps, starting with calculating the water to cementitious ratio, estimating the 28-day strength, and then predicting strength development using maturity growth rates. Next slide, please. This is the example result where we provided specific proportions for the 7 key components of a concrete mixture. When comparing the predictions to the actual compressive strength value from the UCI dataset, the results show good agreement at 3, 7, and 28 days. At 90 days, the maximum difference was around 17%, which could be further calibrated based on local batch variation in real use case. However, since 28 strength is commonly used as a key parameter for structure design, concrete proportioning, and evaluation, it is worth noting that the predictions generated by ChatGPT showed strong accuracy. Next slide, please.
All right, moving on to case study 3. It was durability against chloride degradation and freeze-thaw cycles. So we actually have the example prompt on the screen here, which is to generate a concrete mix that can resist chloride attack and survive freeze-thaw cycles. Give me examples of mixed designs with material proportions. Focus on improving durability and explain your reasoning. So we asked ChatGPT to generate concrete mix designs with these two major durability issues for structures exposed to things like de-icing salts or marine environments. And by using the ACI 318 durability guidelines that we uploaded into the chat, ChatGPT identified some important parameters such as a maximum water to cement ratio of 0.40 and a minimum comprehensive strength of 5,000 psi, about 34.5 MPa, and an air content around 6% for standard aggregates. It also came up with two concrete mix designs, one using fly ash and the other using slag cement, and presented them in a clear table with the correct material proportions. And in conclusion, we showed that ChatGPT can create flexible and explainable concrete mix designs. By embedding ACI standards in real-world data, we improved the accuracy of the recommendations. The system also adapted easily to different project needs like strength, durability, cost, exposure, etc. So overall, this approach supports more sustainable, accessible, and practical construction practices. And here are our references. Thank you.